In the last fifth part of today's lecture, we'll look into decision trees. The nice thing about the decision trees is that they represent the decision, as the name suggests, via a tree. So we can really look into how the decision is being formed. The tree will consist of the inner nodes, which will correspond to features or attributes, the branches, which will correspond to values of the features, and the leaves will correspond to the final decision. So here's an example. These are the features x2, x3, x1, and then for each feature, let's say for x2, there is a set of possible values that the feature can take, and then at the leaves of the tree, there's going to be the labels of the class, the y's, right? And once we have such a tree constructed, then an instance will be classified by comparing its feature values with those of the tree in the nodes and of the branches, and then we'll basically be traversing from the root down to the leaf, where we will be making a classification decision. So starting from the root, we'll basically inspect what's the feature value of x2, and if it's, let's say, v1, then we move on to this node, and then we inspect what's the feature value x3 of the instance, and let's say it's v2, and we end up with y2 as the classification label, right? So upon reaching a leaf, the instance will be assigned the label of the leaf. Here's the decision tree for our example day for beach volleyball, which starts by looking at the weather feature, and then the feature branches into the three possible values: sunny, cloudy, rainy. If the weather is cloudy, we immediately decide and predict that it's a yes. If the weather is sunny, though, then we inspect the second feature, humidity, and depending on whether humidity is high or normal, we would classify the instance into no and yes respectively. And if the feature value for weather is rainy, then the next feature we're gonna inspect is wind. If the wind is strong, we say no. If the wind is weak, we say yes. So for example, if the feature is this one, sunny, low, high, strong, then the feature would be, the classification would proceed as this. Weather is sunny, humidity is high, and then the decision is no. Notice that we actually did not really need to inspect all four features here of the instance. In this case, it was enough, it sufficed to just look at two features. Okay, so that's the basic idea of a decision tree. As you can see, it's actually quite simple and quite intuitive. The very cool thing about the decision tree is that you actually get to see how the decision is being made. And yeah, I guess the only question remaining is how do we actually build such trees from data? Before we actually look into that, let me just say that decision trees relate to what we call rule-based classification, because a decision tree can be thought of as a very compact representation of rules, in which every path from root to the leaf corresponds to one rule in the form of conjunctions of conditions on feature values. So for example, if you look at this path here, it's basically telling you that the weather is sunny and humidity is normal, right? And then you get a yes. The other way you can get a yes is if the weather is cloudy, and then yet another way you can get a yes if the weather is rainy and the wind is weak. So there are like three options in this case to get a yes, and they stand in a disjunction. So basically a set of rules for the same class label is going to be a disjunction of conjunctions, where the conjunction corresponds to one path and the disjunction corresponds to the set of paths, right? So, for example, the rule for yes in this case then would be the following one: weather is sunny and humidity is normal, which is this branch, or weather is cloudy, which is this branch, or weather is rainy and the wind is weak, which is the third branch. Okay, so keep in mind that not only the decision trees are actually nice to look at, and we can actually see how the classification is being done, but even more, they can be converted into a set of rules. And the rules are also a nice instrument to explain why certain decisions are being made. We look into one specific algorithm to construct decision trees from data, and the algorithm we're going to look into is called ID3 algorithm, which stands for iterative dichotomizer 3, which is a simple algorithm proposed by Ross Quinlan in 1986. There's Ross on the left, there's his paper from 1986 on the right. Okay, now as we've seen, classification or prediction using the decision trees is actually quite straightforward. The main question is how to build them in the first place and how to build them from data, because we're doing machine learning. Now, every decision tree is actually partitioning my data, because if you look at the node, what the node does, it divides my data set according to a value of a certain chosen feature, and I get then these partitions, the non-overlapping partitions of the training set. Now, when I do this the division in the children node, I'll keep doing the division again. So basically, I can say that I'm recursively partitioning the data set into smaller and smaller subsets. Now, for every training set, there is going to be a finite number of decision trees that will give me a perfect classification for each instance in my training set, assuming that no identical examples exist with distinct labels. Now, if there are many possible feature values, then the number of such trees actually becomes very large. And in practice, actually, I would be preferring trees with as few nodes as possible, because the simpler trees among the many possible trees will actually correspond to simpler hypotheses. And we already said that simple hypotheses, in line with the principle of parsimony and Occam's razor, the simpler hypothesis will actually generalize better, which is to say they will be less prone to overfitting. So if I can choose, and I can choose because for every training set there will be a finite number and quite a large number of possible trees, I'd like to end up with a tree that's actually as small as possible. Now, all fine, but it turns out that finding a minimum sized tree which still perfectly classifies all the training examples is actually an NP-hard problem. So, if the number of features and possible values is large, there's no chance on earth that we'll actually be able to solve this using exhaustive search. So instead, similar as with the traditional AI, we need a heuristic approach to build the tree that will hopefully get us close to a minimum size tree, but by not doing an exhaustive search nonetheless. Okay. Now, if you think about the tree as a collection of nodes, where in each node we are actually testing for one feature value, then we realize that the tree structure is entirely determined by what feature is tested in what node. And this basically means that when we start constructing the tree, and we start out from the root, for the root we can choose any of the n features. And then once we've chosen one feature, then for the child level nodes, the first level nodes of the root, we can choose between n-1 features and so forth. Now, if we think about tree construction as choosing features for each node, which is a legit way of thinking about it, then the question of how to build a tree basically amounts to the question of how do we choose which feature to use for a current node. And in order to do this, to choose the best feature that will eventually, hopefully, give us the minimum size tree, we need a numeric, ideally, criterion for selecting the best feature by which we'll actually split the data in the current node. And intuitively, I'd like to choose a feature that actually does a good job in discriminating between the training examples according to a label. Ideally, I would be able to choose a feature for my current node that actually divides the examples so that for each of the different feature values, I end up with different labels for these examples. This would be like a perfect split that actually splits the data set by feature value, and the splits correspond one-to-one to the labels. Okay, now let's look at an example. Again, it's going to be the same example as for the need-based classifier, a day for beach volleyball, where if you remember, I am given 14 examples, and each of the examples got 4 features, and there's one final label in my training set, which is a binary one, a yes/no label corresponding to whether the day is a good day for beach volleyball. Okay. Cool. Now, let's say I'd like to build a tree, and I'll need to, the first question then is, what do I put into the root? So which feature of the 4 here, the weather feature, temperature, humidity, and wind, which of the 4 will be actually chosen, should I be choosing for the root node? And as I said, ideally, I'd like to choose a feature that actually does a good job in separating the data based on the label Y. So what I can look then at is, if I take the weather feature, how many of the examples in the sunny branch will actually be yeses, how many will be nos, and I do the same for the other values, and then I do the same for the other features as well. So I end up with a table like this one. If the feature is weather, the feature got 3 values, and if the weather is sunny, then there is 2 yeses and 3 nos in my data set. If the weather is cloudy, there is 4 yeses and 0 nos in my data set, and so forth for rainy as well, and also for the other 3 features. Now, if you look at the distribution of yeses and nos here, and keeping in mind that ideally I'd like to have a feature that does a separation that closely mimics the yes and no label, we can actually see that the weather cloudy does quite a good job here, because if the weather is cloudy, then it's immediately a yes, because there is no cases in this case, right? But as for all the other combinations of features and values, the picture is actually less ideal. If you look at sunny here, it does actually quite a poor job in separating between yeses and nos, since I end up with almost the same number of yeses and nos. And similarly with rainy, temperature high is even worse, because I end up with 2 yeses and 2 nos. Temperature low is actually not so bad, because I end up with 3 yeses and just 1 no, which is not as good as 4 against 0, but still it's actually not that bad. So we actually need to come up with a criterion that actually looks into these numbers. So the split by weather might actually be good, because by the cloudy value it actually does a good job. But then again, we need also to look into the other 2 values of the weather feature where the split is less than perfect. And now we need to come up with some numeric score for weather, for temperature, humidity, and wind, that will tell us which of the 4 to pick for the root node. Okay. Now, as I said, the best split is by the feature for which all examples in each branch belong to the same class, whereas the worst split is by a feature for which in each branch examples will be actually uniformly distributed across all the different classes. Now, there is a measure from a theory of information that I can use for this, and it's called entropy. Because entropy measures the uncertainty of the system, and ideally, if all the examples in one branch belong to just one class, are labeled with one class, then entropy is the lowest. Whereas if they are uniformly distributed across classes, then entropy will be the highest. So my goal, since I'm after the best split here, the best split here would be to minimize the entropy, because if the entropy is minimized, this means that I'm quite certain about what the label of the examples in that particular branch is supposed to be. So the criterion then can be expressed as minimizing the entropy of the labels. Let's define the entropy of the labels or of the data set. So let's say that D contains examples from K classes, where K can actually be more than 2 classes. Then the entropy of the data set will be defined as follows. Now, this is the ordinary definition of entropy from theory of information, where basically I'm computing the probability of an event and then taking the log of that probability and summing across all the possible events, which basically gives me the expected code length of the variable, right? Don't forget about the negative sign here in front. Now I'll do the same for computing the entropy of a data set D. I'll actually compute the probability of the label Y for that class, and here we are going across all the K classes, and then I'll just take the log of the same probability. Typically, the standard definition of entropy in information theory is the dual logarithm. But since we are after the minimum entropy, it doesn't really matter much as long as we're using the same logarithm consistently, the same logarithm basis. As per definition, the case where there is a 0 probability for a class, then basically we'll say that the entropy is equal to 0. Now, that would be a perfect split if entropy is down to 0, because then there is no uncertainty and all the instances belong just to one class, right? Now, if this is not the case, then the entropy is going to be higher than 0. And for the worst split, the most non-discriminative split we can make, the entropy is going to be equal to log of k, where k is the number of classes. Now, in case of binary classification, where there's only 2 classes, like yes and no, where in other words k equals to 2, entropy then is just simply considering the 2 values yes and no. And in this case, the graph of the entropy, where p is the probability here on the x-axis of the, let's say, positive class, looks like this. The worst case entropy, or the highest entropy, is for a 0.5, where both classes are equally likely, right? In this case, the probability is the dual logarithm of the number of classes, which is 2, so that it's basically equal to 1, right? That's the worst case. In case of binary classification, entropy being equal to 1. The best case, as always, is entropy being equal to 0, which will happen either when the probability of the yes class is 0, or where the probability of the yes class is 1. In either case, when we are entirely certain that it's one class or the other. Okay. Now let's look back at our dataset example, where we looked into the 4 features: weather, temperature, humidity, and wind, and their values, and we counted the number of yeses and nos for these features. But now we actually have a numeric score that we can compute, which is the entropy for each of the feature value combinations. So let's do this. Let's look at the first combination here, the weather being sunny. There is 2 yeses and 3 nos, which basically means we would now compute the probability of the class being yes and the class being no. And same as with naive Bayes, we would be using maximum likelihood estimate to compute the probability of yes, which then would be 2 over 5. And the probability of no would be 3 over 5. And then if we plug this into the formula for entropy, we end up with quite a high entropy of 0.971, which also is expected since the distribution is almost uniform. This is in contrast to the weather-cloudy combination, where we got 4 yeses and 0 nos, where the entropy is 0, because all the examples belong to just a single class, and the probability of the no class is 0. And for the rainy weather-rainy combination, we have actually the same situation as for sunny, 3, 2. Previously we got 2, 3, but it's all the same. For entropy is 0.971. And then we would go on and compute these values for all the other combinations. There's some worst case scenarios here where the temperature is high. We got uniform distribution 2, 2, so the entropy is going to be the maximum 1, and same for strong wind 3, 3. The entropy is 1 as well. Okay, so if we now look at these figures here, the entropy values, we can see that actually weather attains the lowest entropy for cloudy here, which is nice, and we already said this is a good thing. This is a good branch. But we also have to consider, when we talk about the value of the feature as a whole, we have also to consider these other two entropies, which actually turn out to be not so small. So, we actually also have to acknowledge the fact that rarely will the entropy of a feature be 0 for all its values, because, consider what this actually means. If you get a feature and all its values, all its branches give you the entropy of 0, this means this is a perfect feature that perfectly correlates with your label y. And then this basically means, you don't need the other features. You actually have your label in the features, which is a weird thing to have. It's just not something that happens in real life. So we will actually be happy with just selecting the feature that reduces entropy the most, while we expect in subsequent nodes to do further reduction of entropy and then eventually reach the entropy of 0. Okay then. With this in mind, we need to come up with a criterion that looks not just at the single feature value combination, but looks at the entire feature and gives us an estimate of how good the split by this feature would be. And the criterion that is typically used, and probably one of the simplest, is information gain. Information gain measures the expected reduction in entropy if we split our data according to a certain feature. And let's look at the definition here. So the information gain, IG for short, will be computed for a certain feature X on a set of examples D. That's my information gain. And the way it works is it looks at the current entropy of my data set. So, current distribution of yeses and nos. And then it looks into a certain feature X and all the possible values of these features. Remember that Vx is the set of values of the feature. So it looks at all the possible values of the feature, and then it basically takes the subset of the set where the feature value X is V, and computes the entropy. Okay, so it basically computes the entropy for the subsets obtained by splitting by each value of the feature. Since there's going to be a number of entropies because there's a number of branches, it will weigh them by the number of instances in this branch divided by the total number of instances. This gives us the relative size of the subset, or it gives us the ratio of examples in a certain branch. And then what it does is it adds up these values for all the branches. Now, in mathematical terms, what it actually does, it computes the entropy after splitting, and it weights this by the probability that an example, because this again is relative frequency, which I can consider as a probability, the probability of an example belonging to that branch, which, if you think about it mathematically, is just the expected value of the entropy, because it's the probability weighted entropies, right? So, what we're actually computing here is we start with the initial value of the entropy, from which we deduct the expected value of the entropy if we use X as a splitter as a feature by which we do the split. So basically, ideally, the entropy after the split would be very low, and if the initial entropy was very high, then the difference here would be actually quite high, right? Because this would mean that we started out from a very high value, and then we managed to reduce to a very low value, and then the information gain here would be high. Okay, so high information gain means that the drop from the initial entropy to the expected entropy after splitting is actually quite high. And that's exactly the feature I'd like to have for my node. Okay. Good. Now let's go back to the example of a day for beach volleyball, and let's try to do the entire example and build the tree for the data set, now using information gain as the criterion for selecting nodes. To make our life a bit easier, let's denote the data set D with mn, where m is going to be the number of positive examples, which is to say the number of examples labeled with a yes, and n is going to be the number of negative examples, which is to say the number of examples labeled with a no. Okay, now we'll start from the initial entropy, the entropy of the initial data set. Initially, if you remember, we got 14 examples, of which 9 are positive and 5 are negative. Now, if you would plug this into the formula for entropy, this is what you get. It's the probability of the positive class, which by maximum likelihood estimation is 9 over 14, and the log of that probability and minus in front, and then the probability of the negative class times the log probability of the negative class, and we end up with 0.94. Remember, 1 is the maximum entropy for the binary classification case. So, if you compare this to 1, it's actually quite high of the entropy, which merely reflects the case that the distribution of examples is actually, well, it's not uniform, but it's not so far from uniform either. Okay. Now we need to select the node for the root node, and we do this by computing information gain for each of the 4 candidate features, right? The weather, temperature, humidity, and wind. So let's start with weather, and this basically means we compute the information gain for weather. So we start with our data set with 14 examples, of which 9 are positive, 5 are negative. And the initial entropy is, as we just said, it's 0.940, okay? And now weather got 4 feature values: sunny, cloudy, rainy. And if we would split by sunny, then there will be 5 examples for which weather is sunny, of which 2 are positive and 3 are negative. And if I would compute the entropy of this, so 2 positive, 3 negative, it would amount to 0.971. Okay, then I do the same for cloudy. If the weather is cloudy, there is 4 examples, and all 4 of them are positive. There is no negative examples, and this basically means entropy is 0. And if the weather is rainy, there is 5 examples again, of which 3 are positive and 2 are negative. It's the same entropy as for the leftmost branch, which is 0.971. So I got the entropies for each of the subsets here. And now I've got the initial entropy, so I've got all I need to compute the information gain. So the information gain of weather on data set D is, the initial entropy is 0.940, and this now will be reduced, so a minus and then a sum of the expected entropies for each branch. For this branch, it's 5 examples out of 14, times the entropy, and then for this branch it's 4 examples out of 14, the entropy is 0. Now this is good, right? Because then this basically means the gain is going to be higher. And then for this branch it's 5 examples again out of 14, the entropy is 0.971. So this is the expected entropy, and minus this, right? And we end up with the information gain of 0.246. Now, is this good or not? It's difficult to say because it's a relative figure. It depends on what the information gain for other features will be, and there's no way around it. We need to compute information gain for the other three features. So let's do this. We've done this for weather now. Let's do the same for temperature. Okay. So, again, the same logic. We start out with 14 examples, 9 of which are positive, 5 are negative. The initial entropy was 9.4. And now if you look at the temperature feature, it's going to split my data set into 3 subsets by high, medium, and low temperature value. If temperature is low, then I end up with 4 examples in my data set, and exactly 2 are positive and 2 are negative, which basically means the entropy is the highest. It's 1, right, since the distribution is uniform. Now that's not good, but let's see what else we got. If temperature is medium, then I end up with 6 features, of which 4 are positive and 2 are negative, and this gives me an entropy of 0.918. And if the temperature is low, then I end up with 4 features again, of which 3 are positive, 1 is negative. This gives me the entropy of 0.811. Again, if I plug this into the information gain formula, I start with the initial entropy here, 0.940, and then I'll be subtracting the expected entropy, which I compute as the number of instances in each branch, 4 divided by the total number that actually did enter this node, which is 14, times the entropy here. And I do the same here and here. I end up with actually quite a small information gain, which basically signals to me that the expected entropy is actually still quite high. So the reduction from the initial entropy to the expected entropy turned out to be quite small. So, temperature is not going to be selected. We already can see that weather is actually doing a better job in splitting the data. But let's look at the other candidates. The next one's humidity. Again, we do the same. We start with 14 instances. The initial entropy is 0.940. That's humidity. Now, unlike the previous 2 features, humidity got only 2 values, high and normal. And if the humidity is high, then it's going to be 7 examples here. And the entropy then for 3 positive and 4 negative ones is actually quite high because this is quite close to uniform. It's 0.985. And for humidity normal, though, situation is actually better. There is 7 examples, of which 6 are positive and just only 1 is negative. So the entropy is lower. It's 0.592. Again, we compute the information gain of the humidity feature on the dataset, which is starting with the initial entropy 0.94 and then reducing this with the expected entropy. We end up with 0.151. Okay, and the last feature to consider is wind. Same logic. Wind will split by weak and strong. There's entropies here that we end up with, and the information gain is 0.48. Now, if you would look at the 4 information gains that we just computed, you realize that weather actually, as a feature, has got the highest information gain, or the largest expected reduction in entropy. So we'll go for the weather feature, and this feature will be in the root of our tree. And now once we've dealt with the root, we can continue building the tree and adding nodes beneath the root node by looking at the remaining 3 attributes, right? So weather has been used as a feature. Next, we look into the remaining 3 features. Okay, so this is our tree as it stands now, the partially built tree. Weather will be the root node, and then weather will be dividing by sunny, cloudy, rainy. And now we need to recursively apply the same logic on each of the subsets in each of the branches. So let's zoom in on this subset here, where we have 5 examples for which weather is sunny, and 2 of them are positive and 3 of them are negative, which will give us the initial entropy of 0.971. Now here's the subset of this data set where the weather is sunny. I omitted the feature of weather in the table since weather is always sunny, right? So the remaining features that we can consider for further splits are these three: temperature, humidity, and wind. And as you can see, there is 5 examples here, 3 of which are negative and 2 are positive. So the question now again is, what is the best feature of these 3, temperature, humidity, and wind, to do the split by? And we'll just do the same thing. We'll actually test each of them in turn and compute the information gain, and then we'll pick the one that maximizes the information gain. So let's start with temperature, okay? But this time around we are working on the subset here, right? Okay, so if temperature is actually the feature that I like to take as the feature for the children node, let's actually look at, if this is the case, I need to compute the information gain from temperature on the subset of weather equals sunny, because I'm now working on the left branch, right? So the initial entropy in this case was 0.971, as there were only 5 examples in this branch where the 2 are positive and 3 are negative. And if I would choose temperature as the feature for that node, then I would be dividing the 5 features by high, medium, and low, so that basically 2 examples would end here, and it's going to be only 2 negatives and no positives, which is good because entropy is 0 in this case. If the feature is medium, well then I end up with 1 positive and 1 negative, which is not good. Entropy is the highest. And if the temperature is low, I end up with 1 feature of which 1 is positive and none are negative, which is good. Entropy is 0. And if I plug this into the information gain of the temperature feature on the subset of instances where the weather is sunny, this is the initial entropy, this is the expected entropy negated, and I end up with the reduction of 0.571. Then I'll consider the next feature, humidity. Essentially, I do the same. Again, humidity, starting with these 5 examples, I would do a split by high and normal. And in this case, actually looks quite good because I end up with 2 branches where everything is clear cut. If humidity is high, then the decisions should be all the examples are negative. If humidity is normal, all the examples are positive, which gives me the maximum entropy reduction of 0.971, right? Because I started with 0.971. The expected entropy is 0, so I end up with the maximum information gain. This is good. Okay, so it seems like humidity is going to win here, but let's also look into the wind feature. And for wind feature, we actually end up with quite a bad split, 1, 1, 1, 2, which gives me quite a low information gain. So we conclude here that information gain, or expected reduction in entropy, is the largest for humidity feature. So we will select that feature for the node beneath the wind equals weak branch. No, not really beneath the wind equals weak branch, but that's an error. But beneath the this branch, weather equals sunny branch, right? Because this is the node, this is the feature we're looking at, and the node we're looking at. Okay, sorry about this. Okay, so yeah, this is then how the tree looks like, right? We've chosen weather for the root node, and we were now looking into this node, and here we've just chosen humidity to be the feature for that node. Cool. Now, once we've chosen these nodes, for all the cases where the entropy is equal to 0, we can actually replace this with a leaf node where the decision is actually determined by the fact that all the instances are negative. This means it's a no node. And if all the instances are positive, this basically means it's a yes node. And similarly, already here at the root, when the weather is cloudy, we have yes instances only, entropy 0. So we can replace, we can put a leaf node here with a yes label. Okay, great. Now we've done, we've completed this part, the left part of the tree. What remains to be done is this. We need to further expand this node since there is 5 examples here, 3 of which are positive and 2 are negative. So the next thing we would be doing here, we would be again testing 3 possible attributes, temperature, humidity, and wind. Which one we'd like to put here. Okay, so in this case, then, as I said, there is 5 examples. The initial entropy of 3 positive and 2 negatives is 0.971, and the 5 examples are the examples for which weather is rainy, and it's these 5 guys here, right? And as I said, we would now test again temperature, humidity, and wind as the ideal splitting features, and then choose one of them based on the information gained. Let's do a fast forward here. And I'll let you just know that we would actually end up with wind as the best feature here. So wind is going to be the feature for this node, and it will be separating the 5 examples into the strong subset and wind weak subset, and we'll end up with leaves here, no and yes respectively. Now this gives us the tree, right? So that's our tree. It's the same as the one that we looked into initially, but now at least we know how the tree was built. Okay, here's the algorithm that does the job of building the tree. Let's look into the algorithm step by step. The algorithm is the pseudocode is formalized by the id3 function, and there is 4 arguments to this function. D is the training set, the set of labeled examples, right? And then there's going to be the parents data set. The idea is that initially we start with D being the entire set of examples, but the function is going to be recursive since we are building a tree here. And then I'll be reducing D to subsets as I move on. And the idea is to have always the parent node subset here so that I can back off, as you're going to see, in cases where I can't do a decision without backing off, essentially. X is going to be the set of possible features or attributes, and Y is going to be the label by which I'm doing the classification. So initially, the parent data set is the same as the entire data set of the training examples. Okay, now the first check here pertains to the case where the data set's empty. There is no training examples anymore. Now, of course, this is not going to happen up front, because if it does, then the algorithm is not going to work, and it's not the point. The point, of course, is that this might happen later on when we recursively partition the data set. So it can happen that I partition the data set and one of the branches actually covers no examples. There is no instances for a particular feature value combination. Now, if what I have to do then is I'll back off to the most frequent label of the parent node, which I'm computing here. The V here is the label that maximizes the number of examples that are labeled with V in the data set corresponding to the parent node, right? So again, if I ever end up with a branch for which there is no examples for that particular feature value combination, then I'll be backing off to the parent node, and I'll choose the most frequent label of the parent node examples to be put as the label for that branch. The algorithm returns a leaf V. A leaf is denoting that I'm building a leaf node labeled as V. Okay, now this covers this odd case here. The second part here is me computing the most frequent label on the current node. Well, initially it's going to be the most frequent label of the entire dataset, but as I'm recursively partitioning the dataset, it's going to be the most frequent label for the dataset, for the examples covered by the node I'm currently looking at. And I'm storing this in V variable. And now I'm checking for two things. The first thing is that the number, well, there's no attributes, no features left. This basically means I am supposed to do a split, but there is nothing I can do the split by. And this will happen if I've got a number of examples with the same features but different labels, because they got different labels, but I can't split them. That's one thing that can happen. The other thing that can happen is that the most frequent value of the label, the most frequent label, is actually if I take the subset of the most frequent label, I get the same data set that I'm looking at, which basically means it's just another way of saying all the examples now have the same label. There is no different labels in my example. This basically signals that the entropy is going to be 0, right? Now, if this is the case, then I'm done, and I will be again generating the leaf with with V being the most frequent label of the current node in this case. And this is where the tree building, at least along that path, ends. Okay, and then lastly, the more general case here is where I am actually branching, right? So what I'm computing here, I'm getting the most discriminative feature by considering all the possible features that haven't been used so far, and those I have in my set X. And then for each of these features, I'm computing the information gain. And I'm choosing the one feature that maximizes the information gain. That's going to be my X variable. And then I will be building the subtrees beneath the node. Initially, I'll set the set of subtrees to an empty set, and then I'll be considering each of the values of the feature I've just chosen based on information gain. So V are going to be the different values, which will give me the different branches beneath the node. And now this is where the recursion happens. I'm making a recursive call to ID3, to the same function, to basically apply the same logic on the subset on each of the branches. So I'm making a call to ID3, but now I am basically partitioning, and I'm looking at the subset where the X feature has a particular value V. In D here, I am giving the algorithm the data set which is not split, so it's going to correspond to the parent node dataset, which I need for this case here, if you remember. And then in the recursive call, I am handing over to the children nodes to consider all the attributes in the set X except for X. So I'm removing that feature attribute, since this is the one that I'm actually now using to do the split, so that the subsequent recursive calls to ID3 will actually look only at the remaining attributes, the remaining features by which to do the split. The Y is just the same, it's just a contextual variable, and it's not changed during the recursive calls. Now each of the ID3 algorithms is going to return a subtree actually, and I'll be collecting these subtrees by appending that tree. Actually, I'll be building a pair here of the value and the subtree so that I have a label on the branch that is leading me to the subtree. So I'll end up with a set of subtrees labeled with branches that lead to them, and I'm generating a node here with the X attribute, which is the one chosen by information gain, and there's a set of subtrees with labeled branches beneath it, which again in turn will also have recursively built nodes and subtrees, and so forth, all the way down to the leaves. Okay, I hope that made sense. And yeah, if it did, then there's just one thing that we still need to cover, and it's the issue of overfitting. You will remember that overfitting is a grave issue when it comes to building machine learning models. And we said that overfitting is about the model being good at the training data, but being poor on unseen examples, which is basically a signal that the model does not generalize. And also, I guess you remember that we said generalization is very important for machine learning. We are actually building machine learning for the sole purpose of the models being able to generalize on unseen data. So if the model is overfitted, then the whole purpose of doing machine learning is actually ruined, right? And you also probably remember that we've been talking about overfitting of the naive Bayes classifier. We said this is related to how we estimate probabilities. But now here with decision trees, we also can have a model that's overfitted, but the manifestation of overfitting is different with this model than with the naive Bayes. I mean, the manifestation is the same in the sense that the model does not generalize, but the reason why this happens is different, right? Now let's look into that. Decision tree built by the ID3 algorithm will always perfectly classify all the examples from the training set D, again assuming no identical examples have distinct labels. Now this will easily lead to overfitting because the model will perfectly classify all the examples in the training set. But you know, this is already a warning for us, since if the model is so good at the training set, it's likely that it's basically overfitted to the training set and therefore it will perform poorly. Now, why is this the case? Why does the model that actually performs so well on the training set perform so poorly on the test set? Why shouldn't it be the case that the model performs well on both the training set and the test set? Now, the reason for this in real life is that in the training data, typically, or in data more general, there is noise, which basically means there is errors in the feature values or in the labels of examples. And if the model is doing a perfect job in classification of the training data, this is only telling me that it actually has fitted to noise. And that's something I'd like not to happen, because if the model has fitted perfectly to the noise, then the noise on the test set is not going to be the same. And that's where I basically lose the generalization ability of the model. Let's look at a very concrete example now in the context of decision trees. So let's assume that D, the training set, is extended with one additional 15th example, and this is my newly added example. Now let's assume that actually the correct label for this example is yes. But due to noise, the label has been flipped and it's now a no. So what I have in a data set is this example with the no label, although in reality it should have been this example with a yes label. But of course, nobody knows that this is noise, except of course for us now, since we just introduced this. But in reality, you can't really tell which of the 15 examples in your training set has label noise and which doesn't, right? That's exactly the problem with noise. You can't really tell it apart from the genuinely labeled data. Now, notice that if this is my 15th example here, and if I would now use the tree that we just built to classify this example, this would actually work quite well in the sense that I would get the correct label, which is yes, right? Look at the example here is sunny, high, normal humidity, and strong wind. If you go back to the tree which we just constructed here, sunny, normal, and here we are, it's a yes, right? So, you know, the tree that we've constructed already does a correct job in classifying the example, right? But now, if you would have this example in your training set with the incorrect label no due to noise, then of course the classification of the tree that we just built would be incorrect. And then the ID3 algorithm would not allow for this. The ID3 algorithm can give you a tree that does a perfect classification, and it would really give you such a tree. So if you would train anew the ID3 algorithm, using ID3 algorithm, on the 15 examples with this example included with the incorrect label no, you get a different tree. You get this thing here. Okay, notice that the tree is actually larger. Then there's one more level than what we had before, so it's a more complex model, and it's typical for overfitting. You get more complex models. And also notice that the tree actually does a perfect classification of the instance, of the 15th instance, which is, sunny and high temperature. We get the no. Now, this is correct from the perspective of the algorithm. The algorithm actually tried to make you happy and give you a perfect classification of the train set, and this is what you get. You get a no since this is what you have in your training set. But in reality, we know that this label is incorrect. It should have been a yes. So what we end up with is a complex tree, which is made more complex just because of the noise in the training set. I would be so much happier with my initial tree, not with this one. Okay, so how do we then prevent this from happening? One thing that you might say, okay, let's remove noise from the training instances. And of course, this would be ideal, but you can't do this because you don't know what noise is and what isn't. So you have to have a way of living with the fact that there's going to be noise in your data, but then again, trying to prevent from the models becoming so complex and trying to, favor the more simpler ones. And when it comes to decision trees, one way we can do this is, well, actually two approaches. We can stop tree growth before the tree is complete, before we achieve perfect classification. That's one way to prevent overfitting in decision trees. The other approach is to allow for the tree to grow as it pleases, and then we get a perfect classification tree, but subsequently we prune the tree by replacing entire subtrees with leaves and putting majority labels for the leaves, or by converting the tree into if-then rules, and we've seen that this is actually quite straightforward, and then taking the rules as input and then eliminating the conditions in the rule antecedents to make rules simpler. Okay, so any of these, the two strategies might work. Now, all fine, but the question then still remains, regardless of whether you do one or you do two, this thing or this thing, how do you actually decide how the tree should actually look like, in the sense of how complex it should be? When do you stop growing the tree? Or if you do pruning, what do you prune away, right? How do you determine the optimal size of the tree that you actually like to arrive at? And now, I've had to tell you, this is actually quite an intriguing question. How do we know that the model is just of enough complexity for the task we're trying to solve? And there's many methods developed in machine learning to deal with this. I'll just give you a couple of ideas. And I'll divide them into so-called intrinsic criteria and extrinsic criterion, just one of them here. And the difference is whether I'm looking at the final label or not. With intrinsic criteria, for stopping the tree growth, I can, for example, define a maximum depth of the tree and simply stop after my tree has reached that depth, and then put leaves there with majority labels instead of developing the tree further. The question then, of course, amounts to how do we know what the optimal tree depth is? Well, in some cases you might know based on experience, or maybe based on the best practices in domain and so forth. And then you might set, your tree depth to 42 because you just know based on some external source of information that the depth shouldn't be above that. Now, frankly, this actually rarely is the case that you actually know upfront what the optimal depth of the tree would be. The alternative then is to look at the number of examples that are covered by each node. And the idea is, if the number of examples in each node falls below a predefined threshold, then you would not expand the tree further. The idea being that, if there's just a couple of examples there, I wouldn't want to overfit by building trees that deal with 5, 6, 7 examples, because I know that it might be noise affecting the labels of the examples, and then the less examples I got, the more the effect of the noise is going to be. So the idea then is, let's say, if I reach the, 10 examples in a node, I will not expand further, okay? And similarly, you can have the reduction in entropy as a criterion, where you basically look at how much the entropy has been reduced, or in other words, you look at information gain. And if the reduction in entropy is smaller than a predefined threshold, then you would stop and not expand the nodes further. Now, these are intrinsic criteria, the three here, and they will actually work well if you have a sense of, what the maximum depth should be and how many nodes to have in the, how many examples to have in a node, and what the minimal entropy reduction should be. But if you don't, or if you like to rely on the labels that you've got in your training set, then you can do this as well. And in this case, you would use an extrinsic criterion for stopping the tree growth, or for pruning the tree after growing the complete tree. Now, you can't really look at the labels in the training set, because if you would look at the labels in the training set, then again you'll end up with a perfect classification tree. You actually are looking you after the question of how well the tree generalizes, and then you have to keep in mind that one way to test the generalization ability of the model is to test its performance on unseen data, which brings us back to the idea which we introduced earlier, that of a validation set, or of doing cross-validation. So the idea is that I will be training my decision tree on the train set, and then I'll be testing it on the validation set which the training algorithm has not used to build the tree. And then I'll do this a couple of times, let's say for different depths of the tree. And then I can decide what's actually the optimal depth, because if the error on the validation set starts to increase, or likewise, if the accuracy starts to drop, then this signals to me that I'm actually going into the overfitting mode, right? This is related to the plot that we've seen earlier. We talked about it. There is the complexity of the model on the x-axis. There is the error on the y-axis, and we're looking at two errors: the training set error and the validation set, computed on two parts of the dataset with no overlap between them. And we said we'll actually look into the complexity here along the x-axis, and we know that as the model becomes more and more complex, the training set error is going to reduce, but that's actually another surprise. What will also happen is that the error on the unseen data set, which is a validation set, will drop at first and then start increasing, and this is where basically the model is overfitting. So the ideal complexity is the one that minimizes the error on the validation set, and it's going to be this one. Now, in case of a decision tree, the complexity can be expressed in whatever way you wish, maybe the tree depth or the number of nodes, for example. If the tree depth is your complexity, then this basically means as you increase the depth of the tree, you go from left to right on the x-axis here, the model is going to become more and more complex. And what you would do then, you would just train a very shallow tree and compute these errors. Then you would increase the depth by 1, say, and so forth, and you would always compute these two errors. And then at a certain point where you notice that the error starts, the validation set error starts to increase again, you would back off to the depth of the tree that gives you the minimal error on the validation set. And that's how you hopefully can prevent overfitting, because you know that you've chosen the depth of the tree that actually gives you the best performance on unseen data, which is to say it does the best job in generalizing. Okay. And some final remarks on decision trees. The algorithm that we have introduced, ID3, is the simplest algorithm for inducing decision trees. There is more complex alternatives out there, such as the C4.5, also proposed by Quinlan, as well as the Quest algorithm, and there's many more. Besides the information gain criterion which we looked at, there's also alternatives. like the Gini index or the chi-square test, which can be used besides or in as a substitute for information gain. It's really hard to say which one works the best. Typically, you would test each of them and see what works the best for your problem. Now, we looked into decision trees with categorical features, that is to say, with features with discrete values. But decision trees can also be used if the features are numeric. In this case, each node would be splitting the data set by a threshold, so that all the examples for which the feature value is lower than a threshold would be then on the left, and all the examples for which the feature value is larger or equal to the threshold value would be put to the right. But essentially the logic is the same as with discrete features. Also, we looked into decision trees for classification. So our leaves have been the discrete labels, the Ys, right? But the decision trees can also be used for regression, not only for classification. And in this case, we're talking about cards, which are classification and regression trees. Now, unlike the Bayes classifier, which we looked into before, a decision tree can't really give you probabilities, right? Recall that a Bayes classifier gives you the posterior probability of the class label given X as input, right? Now with the decision tree, you can't really get these probabilities. I mean, you could maybe obtain them, but it's really a question of how well these probabilities actually correspond to real probabilities. Now, so that's the downside. The strength of the decision tree in comparison to the Bayes classifier is that they are easy to interpret because you get a tree, right? And you see exactly how the data is being partitioned. And when there's a new example that you like to classify, you actually see the path along the tree, and you actually get to see how the classification decision is being made. So if you need to justify the decision, so let's say you are building a system for assessing like credit risk or something, or maybe building a system that's supposed to give a loan to bank clients, and then if somebody gets rejected, then maybe the person would actually like to know why. And if you have a naive Bayes classifier or neural network, then the best thing you can say is, okay, you got rejected, your application got rejected because I was multiplying these probabilities, point what, 0.7, 0.6, and this is what you get. Now, obviously, this is not a very satisfactory answer, and it's much better if you can explain to your clients the decisions of the model based on the tree or the rules that you can derive from the tree, right? And then you can actually say, okay, your application has been rejected because this feature is above that value, and then this feature has this value, and this in combination is a no. So whenever you can actually interpret the decision of the model, we're talking about a glass box approach to machine learning, and it's a nice thing to have, especially if your model is actually making vital decisions that will influence other people's lives. This is in contrast to black box machine learning, where you get the decision, but it's very difficult to justify why the decision has been made. Naive Bayes is one nice example of a black box model, but there's even models that are more black boxy than naive Bayes, say neural networks, where there's a larger number of parameters involved, and then the interpretation becomes more and more difficult. So the advantage of decision trees is that they are glass box. There's one more weakness, though, to decision trees, and that's actually two weaknesses. They're prone to overfitting, which means they're generalized poorly, and they have high variance. Now, being prone to overfitting, we already said this can be addressed using pruning or stopping tree growth and using cross-validation. That's all fine, but nonetheless, in practice, still you would actually end up quite often with a model that's actually either overfitted or maybe not performing that well. The related issue is that of high variance. That's the case of you getting entirely different trees from data set that just slightly differ from one from another. So imagine a data set there, and there's just one example that's slightly different between the two data sets, and you end up with completely different trees. Now, that's not a nice feature to have. We'd like to have more robustness in our model. Now, the last two weaknesses, that of overfitting and high variance, can actually be alleviated by looking at a collection of trees instead of a single tree, and this will give you a more robust model. And the name for this, when we look at a set of trees or set of models more generally, is ensembles. And when we look at a set of or ensemble of trees, we're talking about a random forest classifier, which is actually quite a well-performing model in machine learning. Okay, so that covers decision trees, and it also covers the lecture machine learning. Let's wrap up. So machine learning is about building models that are based on data and that can predict properties of new yet unseen data. We said this is generalization, and it's the main feature, the most important characteristics of machine learning. That's why we do machine learning. There is three main paradigms of machine learning: the supervised machine learning, unsupervised machine learning, and reinforcement learning. And in this lecture, we focused on supervised machine learning, which we said is about training models using examples, and the examples have class labels if we do classification, or they have numeric labels if we do regression. We also said that machine learning models are prone to overfitting, which means they perform well on the data they've been trained on, but very poorly on the unseen data, which means they fail to generalize. And we said this can be prevented by using cross-validation on a validation set. And then we looked into two concrete algorithms. We looked at the naive Bayes classifier, which classifies an example to the maximum a posteriori probability class, and we said this is the map hypothesis. And we also looked into how to train this model, and we said this can be trained simply by estimating probabilities from the training set data, and we do this for the class priors and for the class likelihood. And then lastly, we looked into decision trees, which we said are a model that recursively partitions a set of examples by features and their values. And we also looked into the ID3 algorithm that is selecting the features for each node based on the information gain criterion. There is more complex machine learning models than naive Bayes and decision trees, and we look into one of these, one actually quite a popular one, the neural networks and artificial neural networks next.